Hello, everyone. My name is Saul Haroon with McKim Creed, the National Director of Renewable Energy here in the United States. It's my pleasure to discuss with you interconnecting renewables, distributed energy resources, and some of the challenges on the grid. This is a perspective, a North American perspective, just to be clear. The challenges that we face in Canada, US, and parts of Mexico. So I will be focusing on that. Obviously, there are commonalities in terms of interconnecting renewable resources to the grid, along with Africa, Europe, Asia, and Australia. But the focus today is on the North American grid. So, as I mentioned, I'm the director of renewable energy at McKim Creed, a large engineering consulting firm, and I'm focused on large scale, utility scale, as well as CNI, PV, energy storage, microgrids, and the like. And I've got a considerable amount of experience, 20 years, and I'm happy to share with you a little bit about that perspective of some of the challenges that we have seen in interconnecting that grid. So I apologize if the presentation might seem a little bit rushed. We've got very little time, and I've got many different projects I'm currently working on in interconnection. So I'd like to share from that experience. Initially, I'll present just a quick overview of the landscape of DER, which I think many of you are familiar with. Then we'll dive right into the interconnection functions and the process. I'll give an example of a system impact study, and then we'll look to the future as to what are some of the challenges and how we can perhaps resolve them or mitigate them. There will be two files, two PDFs accompanying this presentation, which I highly recommend you have a look at. One is an NREL document about the whole system impact study, and the other is an actual redacted system impact study example, again, North American perspective, that I think you'll find quite useful. All right, so the landscape, many of you are already familiar with. You already know that we are seeing the DER market, whether it's in US, Canada, Africa, Europe, or wherever, China, etc., on an exponential trajectory. We are seeing a lot more installation every year, utility scale, residential, commercial, CNI, etc. So this is common news, I'm sure, for all of you, not new news. And obviously, economics are driving a lot of this. Standards, codes are also helping considerably. Sometimes policy, depending on where you're in the world, is also contributing to this. Similarly, we're seeing a pattern, a similar pattern with energy storage, that now we're at a point, at an inflection point, where energy storage is truly on a trajectory, exponential trajectory, and I would say poised to surpass PV. It took us this amount of time to get to PV installation, PV deployment on a very large scale, and I think we're seeing that time frame shorten with DER, with battery energy storage, I should say. In fact, to the point that a lot of the work that I'm doing right now is indeed energy storage. So it's an exciting time to see energy storage in combination with PV and also subsequently microgrids. Obviously, pricing has gone down for PV as well as energy storage. You may have heard of levelized cost of electricity. It's one metric to gauge pricing, which is really essentially cents per kilowatt hour or dollars per kilowatt hour. And you want this below the avoided cost or the generation cost for conventional means, whether it's natural gas, coal, whatever it is. And we are seeing that reduce considerably for really low cost. We're seeing that now at around 4 cents or even under 3 cents per kilowatt hour, which is quite impressive. And in parts of the Middle East, I've actually worked in the Middle East as well, we are seeing incredible prices in terms of cost of generation for PV power plants. All right, so diving right into the interconnection functions, what is it really all about? Well, it's about ensuring the safety and reliability. You've got this DER resource. How do you connect to it, whether it's batteries or PV? So you're looking to support this PV generation, PV penetration. You're anticipating additional DER growth. And we're really trying to, part of this puzzle, support a smooth interconnection process and queue management to enable effective, efficient, and cost-effective grid integration, subsequently leading to safety and reliability. This is a very high-level overview of what that interconnection puzzle looks like. And we're going to go into some details, of course. Now, when we're an engineering firm, so we don't do the construction, but we work with EPCs, engineering, procurement, construction firms and developers, who in turn work with these large utilities like Duke Energy, Georgia Power, Southern Power, Southern Company rather, Tampa Electric, all these Dominion Energy and so on, all these various large utilities in the U.S. That have an interconnection process, a procedure outlined. So when system sizes are under a certain size, whatever that might be, there's a fast track process for the interconnection application, particularly for CNI or a small scale utility projects. Then there's a supplementary review screen if the fast track screen fails. If that fails, then there's a full system impact study, which we'll get into what that's about. For large systems, there almost inevitably is something called a system impact study, because large-scale renewables or batteries can have an impact on the grid itself, whether it's thermal overload, voltage regulation, power factor, issues, whatever, and so on. So we're going to talk a little bit about that, what that is about. So here's just an overview of flowchart that we just talked about. So the challenges from a North American perspective about the grid is there can be a lack of grid transparency. The timeline and process delays is not always the fastest in trying to connect these resources. And most interconnection rules in the US are not really updated to adequately apply to, for example, energy storage projects as well. So things are changing, things are evolving, but it can take quite some time to go through this whole interconnection process, to do the system impact studies and so on. Technical requirements, sometimes there's unsustainably high grid update costs, protection, relays, etc., transformers, etc., because the grid was not inherently designed for these distributed resources, at least not here in North America. Incomplete or outdated technical standards. Now, IEEE and NESC and so on, they are coming and evolving these standards, which we'll briefly mention in this presentation. And then what we're also finding is that extensive studies are now required for the interconnection, NERC, and it can often fall to companies like us, beyond the system impact study, which a utility will do, to kind of perform these additional studies to ensure IEEE compliance, 2800, to ensure NERC compliance. I'll talk about that alphabet soup shortly as well. But again, I just want to give you guys a preview as to what we're getting into here. Now, as far as the interconnection studies, what's the main purpose? Is to determine the system upgrades necessary to interconnect the proposed project and the associated cost and construction schedule. So it's a bit of a mouthful, but essentially, once an agreement is entered with the utility, the utility will go ahead and perform some sort of system impact study. Resuming on the system impact study, essentially it's a technical analysis of how a proposed project, most often some sort of electricity generation facility, whether it's DER, renewables, whatever it is, will affect the safety and reliability of the existing electric grid or a larger system. So essentially, it's something typically done by the utilities to see how adding, in the context of what we're talking about, how adding these additional generation resource will impact what's already out there. Now we know that inverters must comply to, for example, IEEE 1547, certainly here in the United States, and now also IEEE 2800 for transmission interconnection too. So that puts some amount of stipulation, some amount of regulation or rules, requirements for these inverters. Now, of course, once you connect this to the grid, there's a considerable other considerations. There's a lot of other things too. Protection, for example. Also, grid stability, voltage stability, frequency, all of that needs to be tested. And if, in terms of thermal overload, load flow, all that sort of stuff is considered, and the utility will perform various studies to see what that impact is at the point of point of common coupling. There is a fantastic document right here that I recommend you look through by NREL, and that is provided as one of the documents as well. That goes into a little bit more detail about that. I also provide an example of a redacted system impact study that I highly recommend you go through. Now, looking at that particular example, in this case, a solar and battery system with a total output of 400 megawatts is at the POI rather, is being considered, and that's what this particular system impact study is looking at. Everything you see right here is a description of what this particular system is, and the report describes the study assumptions, the proposed project, determination of the project interconnection requirements, and estimated costs for integration of the project to the transmission provider transmission system. Fortunately, the report satisfies the SIS requirements of the Idaho Power Tariff. Now, we're going to have a look at a little bit more detail about this study, but various things are considered, thermal overload and that sort of stuff. So if you go a little bit in more detail in the study, you'll see there's a full power flow analysis, a thermal analysis, and overload analysis, particularly when connecting, when power is flowing in a certain direction based on what the loads are and so on. There's protection and controls, which the report surmises, the study surmises, there's adequate load and short circuit interrupting capability on the existing 230 kV breakers. There's also a voltage stability study, transient stability study, and any system upgrades and associated costs are also outlined in this report. Now you can see there's an estimate of any additional cost, and that's coming up to something like $8 million plus. That there was one particular issue here, contingency violations, that if a certain outage happens, there can be thermal overload of a particular feeder line which occurs with single breaker failure in the substation. And so the report does propose what needs to be done on that. So I urge you to look through that. We don't really have enough time to go through this in any detail, but I urge you to look through this report about this typical system impact study. So please do go through that. I did mention IEEE 1547, IEEE 2800 for those of you who are members of IEEE. If you're not, I urge you to do so, to become so. You can dive into great more detail as to what these standards are. So IEEE 1547 applies to DER interconnecting with a distribution system, Well, IEEE 2800 applies to IBRs, inverters, power control systems, and the like, interconnecting with transmission and sub-transmission systems. So there's a little bit more stringent requirement in IEEE 2800 than there is in IEEE 1547. IEEE 2800 provides, as I said, more stringent plant-level requirements for bulk system-connected IBRs and focuses on advanced capabilities and grid support, whereas IEEE 1547 focuses more on the individual unit level of the inverter itself. So please do dive a little bit, into this. And we could spend a whole lecture just in going through like what the voltage and frequency requirements are, the ability for an inverter to decouple from the grid, or rather, let me rephrase that, sorry, to do anti-islanding measures as well. So the inverter is not operating independently when the grid is down, for example. All these particular things are outlined in the standards. You can look at that. The other thing I want to briefly mention, in North America, we have the NERC compliance. So this is a regulatory body that looks at adherence. So let me rephrase that. NERC compliance is the mandatory adherence by organizations, by utilities operating parts of the North American bulk power system to the North American Electric Reliability Corporation, and hence the term NERC, North American Electric Reliability Corporation. It's actually a nonprofit. And these are particular standards. I believe there are over 100 reliability standards to ensure grid security and reliability. And you'll see ones that I often run into, certainly as an engineering firm, we have to do protection coordination, fault recording, so PRC. There are over 19, perhaps even 20 or 21 now, standards within this that we have to test against. We have to make sure things like voltage ride-through, frequency stability, voltage control, all of that sort of stuff is tested. And MOD, also in terms of modeling and reports, we need to provide that. So these are two particular things that we run into, and you'll see a whole bunch of things right here: CIP, sabotage protection, cybersecurity. So essentially, all of this done, these 100 so odd standards within North America, ensure grid security and reliability. And again, this is not just for DER. This is comprehensive beyond just DER. Anyone who's operating a bulk power system and wants to connect to this common grid needs to ensure that there is NERC compliance, right? Particularly the transmission level. In terms of overlap, I really like this little Venn diagram right here. In North America, we have something called the National Electrical Code, which is administered by the NFPA, National Fire Protection Agency. And you guys are also familiar with the International Fire Codes as well. So certain codes, standards, whatever, are there for safe operation, for safety. Others are there for reliable operation, and these are like mandated by NERC, and others are for performative. Now IEC has a whole bunch of stuff too, not just performative, but you can see right here. And you've got an overlap in terms of UL and IEEE standards. I think many of you are probably quite familiar with IEEE, with UL, and with IEC, perhaps less so with NERC and NFPA. So this nice little Venn diagram shows that intersection. So as we're wrapping this up in the 20 odd minutes we've had together, 20 minutes or so we've had together, there are certainly challenges that we have in North America. The grid was not planned, designed, built, or operated with DER, with distributed resources and modern grid aspects in mind. It's very much a push-down architecture here in North America, perhaps in many parts of the world, where power and energy are generated in a central mechanism and then pushed out for transmission and for distribution and load consumption. But now we have a very different type of system where we also need to do load management, demand response programs, smart grid, cybersecurity protection. So, and elements of the grid are involved in maintaining and regulating and ensuring integrity of the grid. So that's a very, very different type of model than what we are used to doing. So we need qualification of the grid, a better understanding and study of the grid. Item number 2 is today's interconnection systems are based on traditional design, grid design and equipment, and on traditional grid operations, reacting to abnormalities and so on, where the old traditional grid interconnection systems were designed to address DR independently from the grid design and operation. So yeah, that is definitely quite a challenge, and we need better standards perhaps. There are standards like IEEE 2030, which talk about microgrid operations as well. So we need manufacturers to kind of step up to the plate as well to help address some of these issues. So tremendous amount of challenges here, but also opportunities. And finally, the grid interconnection systems and DR technologies lack full electrical and integration information analysis tools, characteristics, parameters, models, tools for analysis and integration. So we do need better modeling and simulation improvements towards kind of a more holistic, total integrated electrical systems analysis. So many of you have used tools, and we do too, like ETAP, PSSC, PSCAD, and so on, and we're modeling different aspects or parts of that system. And there are others like OpenDSS from EPRI here in North America. If you guys haven't looked at that, do check that out as well. You can just simply Google, search for EPRI, EPRI, Electric Power Research Institute, and the OpenDSS tool there too. So yes, tools are evolving, but in order to model things like microgrids, smart grids, it is very, very challenging to do so. And we often end up modeling parts of that whole integrated system. So yeah, this is a tremendous amount of stuff going on here. I have been privy to a lot of different tools myself, from predictive production tools like PVSys, Storalytics for storage analysis, Zendy, Energy Toolbase for financial analysis, System Advisor model, and then of course electrical power flow tools like ETAP and PowerWorld and PSSC, PSCAD, OpenDSS, and so on. There is no one tool, no one ring that rules them all, but rather we've got a kind of a patchwork ecosystem here, and we end up using many different tools to try to get a more comprehensive picture. So thank you so much. That was a lot of fun, and we touched upon many important topics of interconnection. You guys got to see a little bit about what interconnection looks like right here, some of the governing bodies that help with that, some of the codes and standards, and I've certainly provided you with some good reading material. So have a look at the article from NREL on overall and system studies and so on, interconnection, and then look at that particular system impact study from Idaho Power. Well, thank you so much. Really appreciate it, and all the best in your continuing education and continuing work all throughout the world. Thank you.